Hello, my name is Leslie Winnick, Director of Alumni and Student Class Outreach at the Stanford Alumni Association. I would like to personally welcome you to the 2016 Classes Without Quizzes series from Reunion Homecoming, a sequence of faculty-led talks designed to reconnect alumni with Stanford. This segment features Professor Joe Boaler's lecture, Mathematics Revolution, Helping Children Learn and Love Mathematics. Joe Boaler is a professor of mathematics education and founder of YouCubed, a new center at Stanford that gives teachers and parents the resources and ideas they need to get students excited about mathematics. She also serves as an advisor to several Silicon Valley companies, and she is a White House presenter on Girls and STEM. Enjoy the talk. We're so glad you could tune in.
So I'm going to be talking about something today, sharing some recent brain science with you and talking about what we know about mathematics learning. Starting with the importance of getting rid of a myth that's very widespread in this country, and it is this myth, the myth of the math brain, that some people are born with one and some people aren't. Turns out most students believe this. It limits their achievement on a daily basis. And we have incredible evidence now from brain studies that actually all brains can grow and change and anybody can learn whatever they want to learn. But that myth is very strong, and we do a lot of work to try and eradicate that, and you'll see some of that as I talk. So what do we know about the brain? It turns out the brain is our most complex organ. It's made up of over 100 billion neurons and several thousand connections between them. And it's also our most changeable organ, we now know. We also know that when learning happens, a synapse fires in the brain. It's like an electric current that moves between parts of the brain. And that synapse, when you learn something, will form a very delicate pathway in the brain. If you go back and learn something more deeply, that delicate pathway will turn into a permanent brain pathway that you can continue to use for the rest of your life. And we also know that if you don't go back to the idea, synapses are a little bit like footprints in the sand, in that if you never return to that idea, if the synapse pathway will just wash away. The brain's very efficient at only keeping what it needs. So some of the major evidence that came for this area that's known as brain plasticity came from my hometown of London, and I'm sure many of you have travelled in these or know of London black cabs. Probably the most professional cab service you can find, and long history in London, currently under threat from Uber, but that's another story. But what I didn't know, and you may not have known, is that to become a London black cab driver, you have to go through extensive training. Many of them train for between 4 and 6 years to become a black cab driver. And at the end of that period of time, you take a test, which is just beautifully called the knowledge. And to pass the knowledge, you have to have memorized 25,000 streets and 20,000 landmarks in central London and every connection between them. The average amount of times it takes to pass the knowledge is 12 times. And you can imagine that taxi drivers don't learn this by sitting down and trying to blindly memorize it. They have to drive these routes over and over and experience them. But the brain scientists became interested in the brains of black cab drivers, and what they found was at the end of this complex spatial training, the hippocampus in their brains has significantly grown. And the hippocampus is an area of the brain that's specialized in spatial information. When they retire from being a black cab driver many years later, the hippocampus shrinks back down again. This is not to do with aging, you'll be pleased to know. It's only to do with not using those spatial pathways anymore. And around the same time that this evidence was coming out from the black cab drivers, a 6-year-old girl actually had half of her brain removed, a hemisphere removed, because she was having fits that doctors couldn't control. And the doctors expected her to be paralyzed for many years, possibly her whole life, because the brain controls your physical movements. But she stunned the scientists, because within months she was running around again. And they could only conclude that this missing side of her brain had in effect regrown. And then a study I want to share with you that comes from Stanford Neuro Labs. It's very recent, you probably won't have seen this, that I think is so important. They brought kids into the brain labs, children between the ages of 7 and 9 years old. Half of them had been diagnosed in school of having mathematics learning disabilities, half of them didn't, and they got these kids working on maths with brain scans. Lo and behold, they found that there were actual brain differences between the kids with learning disabilities and the others. But the difference was this: the kids with the so-called learning disabilities had more going on in their brains. More areas of their brain were lighting up when they worked on maths. And we might think of that as kind of counterintuitive. You think of kids with special needs as having maybe less going on in their brains. They actually had more going on in their brains. But we don't want that. When you work on a maths problem, you don't want all of your brain areas to light up, some of them. And what the researchers did was they gave tutoring to the two sets of kids for 8 weeks. Both of them got the same tutoring with number lines and other sorts of maths. At the end of that 8-week period, not only did the two sets of the kids have the same achievement, but they had the exact same brain functioning. So this is just one of many studies that's coming out that shows us that a very short intervention can change kids' brain pathways. Unfortunately, though, schools are set up on this idea of deciding who can do maths and who can't from an early age and teaching kids differently, and this is what we're working to change. So you may know of the work, it's very famous now, of Carol Dweck, who's also at Stanford, and her work on mindset. And she has shown over many years that everybody has a mindset. You do, I do, kids do. And people with a growth mindset really believe that they can learn anything. But people with a fixed mindset think that their intelligence is more or less fixed, that there's not a lot you can do to change that. Turns out which of those beliefs you have will change your learning pathway. And we have a lot of evidence now that tells us this. This is the maths grades of kids going through 7th and 8th grade. The only difference between these two sets of kids was their mindset, what they believed about their own potential. And you can see it's kids with a fixed mindset who stay at this lower level, but kids with a growth mindset are going onwards and upwards all the time. Turns out your mindset's very important, and it's particularly important for girls and for students of color who have more fixed mindset thinking than other students. So one myth that we're trying to change is this idea of the math brain. A related myth I learned from my Stanford students. So I teach undergrads at Stanford, and over the years, a number of them, I've said to them, are you going to take more math classes at Stanford? And a number of them have said to me, I'll take math classes until I hit my wall. And I say, your what? And they said, your wall. Everybody has a wall. You can go so far until you hit your wall. Well, it turns out there is no wall. I didn't know who this was, this guy. Somebody gave me this image, but I've since learned that this is Kool-Aid Man. My daughter, who's sitting here, actually gave me Kool-Aid last week, and we both thought it was disgusting, but we learned afterwards that you're meant to add sugar, which we didn't do, but anyway. But anyway, this is Kool-Aid Man, and Kool-Aid Man is helping us dispel this myth, and it's a real myth. I was presenting to Cornell's math department a few weeks ago, and one of the mathematicians said, are you serious? There's no wall? Because, I'd given up on this math problem I'd been trying to solve for a couple of years because I just decided I could never get there. And I said, yeah, I'm serious. But anyway, I wanted to share with you a short film. I'm fortunate these days to be working with a filmmaker, and she's the filmmaker who made Race to Nowhere. And she's working now on a film just about maths. And she's doing that because she knows that math is a subject that stops kids graduating college, stops them going to college. And she came down to San Diego, and at the time I was working there with a group of middle school maths teachers to change their teaching. Kathy Williams, who's also here, is the co-director of YouCubed, and she was the director of maths at the time in the district. And together we worked with the teachers to change. And you'll hear a bit from some of the teachers in the school and some of the children in this. It's a 2-minute clip.
In the United States, people think people have a math gene. Either you're born with it or you're not. If you don't have it, then you just don't have it.
Teachers believe that, parents believe it, students believe it. And it's one of the reasons that we have such widespread math failure and math trauma in the States.
I hated math. I absolutely hated it. I felt like I was I wasn't nothing. When I went into other classes, I was like, well, I'm already failing in that class. Why don't I just fail in these classes? I wouldn't really try, and I wouldn't push myself.
It's amazing how many teachers have said to girls, don't worry, you don't need to be good at math. Math isn't your thing. Don't worry about that. When kids get the idea that they're not a math person and they start this sort of downward trajectory, many careers are cut off from them. And this happens to a lot of women, unfortunately. Their career options shrink massively. So we have a situation now where most engineers and most people who work in computer science are men.
I hated math, to be honest with you, when I was younger. I felt that I couldn't do the problems quickly, and I thought you had to do them really fast. I think a lot of students come in with some of the same ideas that I had as a middle school student. They think that if they make mistakes, that means that they're not smart. Working with Joe has been really helpful in breaking down those stereotypes.
So what do you mean when you said it's not working?
Wait, did you just add the
Can I borrow this really quick?
Yeah, and shoot her question.
I have like a connection with math now, definitely. Like, it's like I'm open and I feel like alive, and like I'm definitely like more energetic in science. We use math a lot, and I feel like when they bring up math subjects, I'm like, oh, I learned that already. I could be open to like learning new things.
Well, that's we're trying to get multiple methods.
Yeah, we're trying to figure out.
We'll hear a little more from those students later, but one of the messages that we work to get out to students is this one, that we now know that mistakes are a really powerful process in your brain and make your brain change and grow. So this study is pretty incredible from Jason Moser. What they found was people had MRI scans and they took tests. And what they found was when they made a mistake in the test, synapses fired in the brain. When they got work correct, synapses didn't fire. And so when I share this with maths teachers, they will often say to me, but surely you have to work through the mistake and get it right for synapses to fire. But actually, no. What they found in the study was there were two possible synapses. The first one came when people made a mistake, and the second one came if and when they became aware they'd made a mistake. So then people say to me, well, how can your brain change when you make a mistake if you don't even know you've made a mistake? But the best evidence we have on this is your brain changes when you make a mistake, even if you don't know you've made a mistake, because those are the times when brains are struggling. And times of struggle and challenge, when you're finding work really difficult, are the very best times for brain growth. I was sent a video. I thought I'd share a little bit of it with you from England this week. Our newsletters are actually opened in over 120 countries, and England is one of them. And these are some kids who've been given these messages about mistakes. I thought you'd like this. Also from that study that's pretty amazing, I think, is they found this. These were voltage maps of people's brains in the study. These are the people with a growth mindset when they made a mistake. And you can see the brain activity. It looks like the brains are on fire. People with a fixed mindset did not have as much brain growth when they made a mistake. This tells us something, I think, very important that brain scientists have known for a long time, and that's this. What you believe about yourself will actually change how your brain works when you're working on something. And this is important for all of us. It's very important for kids in maths classrooms, but it's important for everyone. It tells us that if you go into a difficult, challenging situation, and you think to yourself, I know I can do this, but then you mess up or even fail, your brain will react differently, better, than if you go into that situation thinking, I don't think I can do this. That's how important it is that you have self-belief, that kids have self-belief. It actually changes how much your brain will grow. And this starts to help us understand why it is those kids with a growth mindset are always going onwards and upwards. When they make mistakes, their brains are doing more for them than the kids who have a fixed mindset. So we need to change these messages that go out to kids, that, people have a math brain or they don't, or that intelligence is fixed. And one of the ways in which we give these messages are these labels that are used in school. We now know that this idea of being gifted is harmful for kids. A really interesting study that was done, published in the premier journal Science. And what they did was they interviewed university professors to find out how much they believed in the idea of the gift. And what they found was that the more any field valued the idea of the gift, the fewer women and the fewer African American students were in that field. And that held across all 30 fields they looked at. Pretty amazing. You can see a bit here. These were the graphs of the subjects they looked at. The top set is STEM, and these are humanities. So you might notice straight away that math is the one with the more professors believe in the gift than any other subject. The y-axis is telling us the proportion of women in the field. Interestingly, philosophy, similar to math, turns out philosophers believe you have to have a gift to learn philosophy. Interesting also, you can see neuroscience right at the other end of the spectrum. They know there's no gift, so they don't believe in it. But what we have to think about this is this. If professors' ideas of giftedness are harming adults to this extent, what are they doing to young children? And this is where the idea of a gift is harmful. Obviously, if you're a young child, you get the idea you haven't got gifts. That's pretty harmful. But even if you're somebody who's been told you have a gift, many of you here were probably told you had a gift, you were in gifted talented programs. But the problem is if you're given that message that you have a special brain, you have a gift, when you struggle on something, that struggle is devastating. And, this came up this past week with one of my teacher candidates at Stanford who's training to be a maths teacher. She said to me, my whole life, everybody said I had a math brain, I had a gift, I was special with math, I went to UCLA, I enrolled in a math major. And then as I got into high-level classes, I started to really struggle. So I dropped out of the math major because I thought I don't have a math brain. So this is why, we have to get these very fixed ideas out. And, well, before I get onto that, I wanted to share this study with you. It just tells us again how important these messages kids carry around are. So this study was an experimental study. And they had hundreds of high school English students, and all these English students had written an essay for their teacher, and they'd all received critical diagnostic feedback. About half of them received a message at the end of this feedback, half of the kids. And the kids who got that message achieved at significantly higher levels a year later. They had a one-sentence difference in their feedback, but the message that the researchers put at the end of the feedback, teachers didn't know who got it, but the message they put at the end of the feedback for half of the kids was this. At the end of the teacher's feedback, it said, I am giving you this feedback because I believe in you. And the kids who got that message did significantly better a year later with no other change. So when I share this with teachers, I say, I'm not telling you this so you put at the end of every kid's feedback, I'm giving you this feedback because I believe in you. One of the teachers said to me, we don't put it on a stamp. I said, no. Don't put it on a stamp. But so that teachers, and this is true for parents too, know that your words really matter. And we know that kids are sitting in classrooms all the time thinking, what does my teacher think of me? Why did she give that question to that person and this question to me? And we can be saying to kids all the time, I know you can do this, I believe in you. It's a very important message. So another thing for parents that you might find helpful is we now know that one of this little innocuous word of smart is one of the ways kids develop fixed mindsets. In the US, parents praise their kids for being smart all the time. You hear it everywhere you go. I hear it all the time on campus. We now know, though, that what kids hear when they're praised for being smart, when parents praise them for being smart, at first they think, oh, good, I'm smart. But then later, when they mess up, they think, oh, I'm not so smart. And they're evaluating themselves on this fixed idea. We know it has an immediate impact on kids. In one of Carol Dweck's studies, they had 2 experimental groups of kids. They all worked on maths questions. Half of the kids were praised for being smart at the end. Half of them were praised for working hard. And then they were all offered a choice between an easy or a hard task. And the kids who were praised for being smart, 90% of them chose the easy task. And the converse was true of the other kids. I also, I find it's a pretty crude word. It kind of narrows how we speak. In my undergrad class, or in all my classes here at Stanford, I say to everyone, let's not use it. Let's not use that smart word. It's very hard for everybody because they're so used to saying, you're so smart, you're so smart. But actually, when we stop and say, okay, we're not going to use that word, they'll replace it with what they actually mean. And there are much better descriptions. And they'll say, oh, no, what I actually meant was, that's a really nice piece of work, or that was some really nice thinking you did, or that was a really creative solution. And it's really a good thing. They're also on beliefs that may be interesting to you. We know that what parents believe about math changes their children's achievement. And in a study of grade 1 and 2 students, the amount of maths anxiety parents had predicted their children's achievement during the school year. Nothing to do with maths knowledge. Didn't matter how much maths they knew. It only mattered whether they felt anxious about maths. But this is interesting. It only mattered if they helped with homework. So this is an interesting one, and it's really telling us again, you can imagine if a parent has math anxiety, but they never interact around math with their kids, then probably they don't pass that on. But if they help with homework, they're probably saying things about math and that will have this impact on kids. And again, it's telling us this, that what kids believe is really, really important. And we've focused for so long in education on the right way to introduce math concepts, and you know all the arguments about the standards that are out there, when we have been ignoring the fact that kids are sitting in maths classrooms, most of them thinking, I'm not a math person, I can't do this. And until we change that, we will always have widespread underachievement. It's very, very important. So we're actually going to look at some maths together in a minute, but before I do that with you, I want to share one last piece of brain science, and it is this, that we now know that speed and pressure actually blocks the memory, stops kids being able to process mathematically. This is an image of the brain, and you can see here the working memory. This comes from Sian Bylock. And the working memory is where we process math facts. So if I was to give you a math fact question now, your working memory would be really hard at work processing the math facts. But it turns out that when you are stressed or anxious, your working memory becomes blocked and you can't access it. So what do we do to little kids in classrooms from our local school district? 50 questions to do in 3 minutes. From first grade upwards. These are the early onset of math anxiety for kids. We have to get them out of schools. And we're working hard to do that. But in our country right now, maths teachers and many people associate math with speed. They think that to be good at math, you have to be fast at math. What's ironic about this is mathematicians, who we may think of as the highest math thinkers, turn out to be not very fast with numbers. And I work with many mathematicians, and many of them just openly say, I'm very slow with numbers. They're slow because they think deeply about math. And one that I like to share is a quote from a Fields Medal winning mathematician. His name's Lawrence Schwartz. And he wrote an autobiography because when he won the Fields Medal, he wrote an autobiography sharing that when he was in school, he actually felt stupid because he was one of the slowest math thinkers in his school. And this is from his autobiography. He says, I was always deeply uncertain about my own intellectual capacity. I thought I was unintelligent. And it's true that I was and still am rather slow. I need time to seize things because I always need to understand them fully. Towards the end of 11th grade, I secretly thought of myself as stupid, and I worried about this for a long time. I'm still just as slow. At the end of 11th grade, I took the measure of the situation and came to the conclusion that rapidity doesn't have a precise relation to intelligence. This is important. What is important is to deeply understand things and their relations to each other. This is where intelligence lies. The fact of being quick or slow isn't really relevant. So we wrote a paper, we put it on our website. You can find it if you'd like to get some more info on this or you'd like teachers to read it. It's really written for teachers and it summarizes the brain science, but then it also puts in activities that help kids learn math facts, but learn them in a really good way rather than through fear and anxiety. This paper has had about 1 million downloads on our website now. It's been used across the United States to pull time tests out of districts, so that's great. But we generally need to stop associating math with speed and stop discouraging those slow, deep thinkers. I have an article in here, this month's edition of Scientific American Mind, which is an analysis I did with one of the PISA analysts, showing that we analyzed 13 million students' approaches to math through the PISA data set. And what we found was that the lowest achieving kids in the world were the kids who take a memorization approach to math. So if you want to read more about that, it's online.
Hi, you're listening to KCSU Stanford 90.1 FM. We're broadcasting a talk by Stanford professor Joe Boaler. The talk is called The Mathematics Revolution, Helping Children Learn and Love Mathematics. The talk was given during Stanford's 2016 reunion homecoming weekend.
But what I'd like to do now is have us think together about a math problem. Who feels really happy when I say we're going to do some math? Good, some of you. So the reason we're going to look at some math together is this. If we want to change kids' mindsets, we have to change the way they think about math in classrooms. Because when you continually give kids these short, closed questions in math, those questions themselves give fixed ideas about what math is, that you can do it or you can't. So we have to open up math in classrooms. And I want to illustrate this for you, but right now in the US, most math classrooms, unfortunately, offer math more as a performance subject than a learning subject. And what I mean by that is, you ask most kids what they think their role is in math class, they'll tell you it's to get questions right. They don't say that about other subjects. They'll talk about the breadth of the subject. And this really came home to me when a colleague, Rachel Lambert, had said her 6-year-old son had come home saying he didn't like math. And she said, why? What's going on? And he said this. He said, math is too much answer time and not enough learning time. So we can look at that and go, wow, that 6-year-old's very reflective. But actually, kids know. They know from kindergarten up that when it comes to math, it's different. It's about performing and answering questions. So as I share with teachers, we have to give kids tasks that have space inside them for learning. And I want to share one with you now, and it's a task that I'm going to give you to look at individually. And I'd really like you to just think about it on your own at first, so not talking to other people. And it looks like this, so I'll explain this a little bit to you. What we have up here is 3 cases, case 1, case 2, and case 3. And in case 2, there are more squares than there are in case 1, and in case 3, there's even more squares. And I want you to think about this entirely visually, with no numbers at all. So if you're a maths teacher, this is going to be hard. So banish numbers for your mind. I just want you to think visually. And the question is, where do you see extra squares? There are extra squares in case 2, and there are extra squares in case 3. Where on the shape are they? So I'd like you to think about that on your own. Feel free to draw on the piece of paper. And the question is, where do you see the extra squares? And when you think you can see where the extra squares are, feel free to talk with the people around you about where you see extra squares. So I'd love to know how you thought about this problem. One reason I really like this problem is I've given it to many different people now, elementary school students, to Stanford undergrads, to teachers, to CEOs of businesses. And what's really interesting about it is people see it in different ways. So I want to share with you some different ways people have seen it, and I want to find out how you saw it. So, and I ask people when they share their ways of seeing it to also name the methods. And it was my undergrads at Stanford who named this method the raindrop method, where they saw like cubes coming down or squares coming down on top of the shape. Who saw it in this way, the raindrop way? It was also my undergrads who saw this as the bowling alley method, like a row of skittles coming in, like in a bowling alley. Who saw it in this way, the bowling alley way? It was a teacher who said to me, no, it's like a volcano. It erupts and the lava comes out. This is kind of a center-leading way. Who saw it in that way, the volcano way? There's a teacher also who said, oh, no, it's like the parting of the Red Sea. The shape splits and duplicates, and a new center comes in. Who saw it in this way, the Red Sea way? Some people see it as a growth of triangles. They see the whole outside shape growing. Did anybody see it in this triangle way? Similarly, some people see what the empty triangles, what we call in maths the negative space, that grow on the side. We have cultural differences. So when I go to different places, people see it differently. When we were in Boston, we got this method, which I don't get here in California. One of the teachers said to us, oh, it's like snow. It's like the buildings that are emerging out of the snow after the snowfall. When I gave it out to my teacher class recently, one of the young men said to me, oh, I can see the Minecraft tree. There it is, and this is his. So it's like the shape grows from the side. Did anybody see it in that way? It was a teacher in New Mexico who said to me, oh, it's like Wayne's World, stairway to heaven, access denied. And then another one that's interesting is this one. If you move the red square, if you look at the first shape over there and move the red squares each time, you'll see that you can rearrange the shape as a square. Did anybody see it like this? So this is what I wanted to share with you about this maths problem. When this problem, it's a pretty common problem in maths classrooms, but it's usually given out in the introductions to algebra, and it's given out with the request to count. People will say, how many are in the 100th case, or how many are in the nth case? And what happens is kids will count, and they'll say, well, in the first case there's 4, in the second there's 9, in the third there's 16. They might stare down the columns for a long time and see that you can add 1 to this number and square it, then you will get the total number of blocks, which is why we get n plus 1 squared. I gave it out to a big room of teachers one day, and there was a table of teachers, high school teachers actually, who did not listen to my request to look at it visually, and they did this. They drew out a table, they put in the numbers, they said, it's n plus 1 squared. They called me over, they said, we're finished, it's n plus 1 squared. And I said, okay, so why do you think this is squared? Why do we see this? And they said, I don't know, no idea. So this is why it's squared. This is why you see it grows as a square that's always 1 bigger than the case number. In case 2, it's a 3 by 3 square. And in fact, every different way you saw the expression, we could have represented algebraically. And we would have come up with a whole load of different algebraic expressions, but they would all be equivalent to n plus 1 squared. So when we give this task to kids, we ask kids to visualize it first. They have these amazing, rich discussions with each other about the different ways they see it. They understand, our kids understand why it's n plus 1 squared. They know, and they develop an understanding of functional growth that you just don't get from staring at columns of numbers and moving algebra around. So this is part of our approach that we teach, that math should be visual. And we now have more evidence of this, although we didn't know this at the time, but really interesting work that's coming out just very recently. I just published a paper, actually, that for the first time with a neuroscientist, and it shows this, that when we work on maths, even at just doing an abstract calculation like 5 plus 8, 5 brain networks are involved, and 2 of them are visual, the ventral and visual pathways. And in fact, the dorsal visual pathway is the main brain region for representing quantity. So thinking visually is very important for the brain, and improving maths achievement actually means improved communication between these different areas of the brain. Not what happens in schools, which is that we just continually strengthen abstract number areas of the brain, but that we're getting these different brain areas to communicate with each other. And what the brain scientists know is that as children get older and develop, the brain becomes more interactive, and it starts communicating more. The connections, particularly between symbols and visual representations of numbers, get developed. And it is that communication that's really important for maths achievement. So our brains want to think visually. You may have grown up thinking, I'm not a visual thinker, but even if you think that, your brain wants to be thinking visually about math. And we wrote a paper on our website that's really saying, let's make maths a lot more visual than it is. It's called Seeing as Understanding, and it has a range of activities. But one piece that's in the paper I wanted to share with you that's so stunning, I think, and it shows me just how important it is to get research out to teachers and parents. And it is this research that says this, that when we calculate, if I was to give you a calculation to do now, your brain would actually see fingers. And the harder the calculation I give you, the more your brain will see fingers. There are 2 areas of the brain, one that lights up if you use fingers, and the other one lights up when you do a calculation, even if you're not using or thinking about your fingers. And here are some pretty stunning facts about what's known as finger perception. So the scientists call it finger perception, and they say that you need good finger perception, and the test for finger perception is this. If you put your hand under a book or something else where you can't see it, and somebody touches the fingertips, the test is to be able to tell which fingertips are being touched. So it turns out that as you improve your finger perception, your maths achievement goes up. College students' finger perception predicts their calculation scores. And finger perception in grade 1 is a better predictor of maths achievement in grade 2 than test scores. Pretty amazing stuff. And what's incredible to me is you'll know that people do not value fingers very highly out there in the world, but the brain scientists have known this for a long time. And in fact, in 1999, 15 years ago, this leading brain scientist said this: without finger perception and counting, numbers will never have a normal representation in the brain. But what's happening around the country in schools and homes, people regard finger use as babyish. Students are told sometimes they're not allowed to count on their fingers. When we stop kids using their fingers, that is like halting their mathematical development. So it's, very, very important that we encourage finger perception. And in fact, the neuroscientists' conclusions are that fingers should be the link between visuals and numbers. This is the most important manipulative we have, and we should use them. Fingers should also be the support for learning arithmetic for kids. And this last recommendation almost makes me laugh. They say schools should have a greater focus on finger discrimination. And no school or teacher we've spoken to yet knows what finger discrimination is. So we wrote an article for The Atlantic, and actually there is an article in the Wall Street Journal today on this. And it's online today, it's going to be in print tomorrow. Exactly the same, why the importance of finger use in maths classrooms. And on our website and in our papers, we published activities for teachers and parents to do to help with finger perception. So this is one of them. It comes from the neuroscientist training, what they use to train finger perception. And you give kids different colors to put on their fingertips and get them to trace colors. This is the reason that musicians have higher maths achievement. A long time people have wondered about this, thought it's to do with patterns. Probably is partly to do with patterns, but this is a big part of it. So other activities we get kids to trace and do other things. One last thing I think I'll share before I get into some resources that I want to share with you is this. When we present and I share with people the importance of doing open, creative, visual maths, which is what we do, people will say to me, but what about practice, right? You want practice, we want kids doing things like this. Well, actually, practice is good, as I talked about those light pathways that need to be strengthened, but this is not good practice. This is sort of mindless, this is the soul-destroying stuff that kids get sent home. My daughter will tell you about this. That is not good practice, actually. And what is productive practice is when people get to see an idea in different ways. And when it's better as a teacher not to give 40 questions that look the same, but, you can give 4 of these questions and then ask kids, can you write about this situation? Can you draw a picture of it? Can you illustrate it? That will get the brain crossing going on. It will get kids practicing and thinking about the idea. And that is what productive practice is. So other things that have kids practice well, if you do have kids at home that you want to give more practice in math, these are really good apps and games. Most math apps and games out there are very low quality. They just have kids practice arithmetic at speed. Sometimes they have fluffy pandas and things, but they're not good mathematically, but these are really good apps and games you can try. So I want to, before we go, tell you that we brought 81 students onto campus last summer, and we taught them in this way. We gave them all the mindset evidence. We told them there's no such thing as a math person. On the first day of camp, I did presentations with each group. I showed them the kid with half a brain. They loved the kid with half a brain. They spent the whole summer saying, if that girl with half a brain can do it, then I know I can do it. And we taught them math for 18 days here at Stanford. These were our 81 kids. These are a pre-test they took in the district before they came to us, an algebra test. And you can see we had a wide range of achievement from high achievers, the kids who got 0 on the pretest. We grouped them together. We taught them together. 18 days later, they had maths class in the morning with myself and other teachers. And in the afternoon, my undergraduate class took them around campus doing more fun things. This was their pretest. 18 days later, they took the same test. And they'd improved by an average of 50%, equivalent to 1.6 years of schooling. So these were the kids. This is them wearing their YouCubed t-shirts, making our logo. What happened for these kids was this. Every one of the 81 kids told us on the first day of camp, I'm not a math person. They could name the one kid in their class they thought was a math person, the one who shot their hand up. So we changed their ideas. We changed their beliefs. And then we taught maths differently. This is one of the kids saying, they taught us how math is for everybody, and I believed that I wasn't a math person before, but now I believe that anyone can do math, and that helped me a lot. And the way I thought math was about right answers and wrong, but it's really about ideas, it's very creative, and that helped me like it a lot more. We made a website. We had our greatest month last month ever. We had 3 million people coming to the site, where we have a lot of different resources that you might find useful. We have an online class for teachers and parents. I have a new book, which is out. We have a little class for students that has an incredible impact on kids. It's 6 short lessons that are designed to give them a growth mindset, and we have amazing data from that, which I won't go into now. But there's a TED Talk. This is the 12-minute version of this. We have weeks of lessons on the site that, after taking, kids change their mindset and ideas about maths. And then the last thing I want to share is when we make these changes for kids with maths, it doesn't just change their test scores. It gives them a whole new outlook and way of thinking about maths. And we hear them talking about amazing ways when we video them. And I want to share just one last clip now of a boy who comes from that film we saw at the beginning, and this is my last slide. If you don't believe me about what these changes mean for kids, come back and listen to this clip here.
Math class last year was notes and just handouts, and you were your own little box. You were just boxed in. You were like by yourself. It was every man for themselves. But now this year, it's just open. We're a whole big, it's like a city. We're all working together to create this new, beautiful world. I think the challenges and, the future that lies ahead for me, if I keep on pushing, if I keep on doing this, someday I'm going to make it.
So that's all I have to share with you. I'm going to put the lights back on. Thanks. We have about 5 minutes for questions. If anybody has a question, I'd be happy to answer it. Yes, at the back.
Hi, I'm Jordy, class of 06, and
excellent.
I'm a math science tutor from Dallas. And I've been working with a girl extensively who is homeschooled and has dyscalculia. And I was wondering if you could kind of talk to that, because I hadn't really ever heard of it before. I'd heard of dyslexia or ADHD. So I just wanted to kind of hear your thoughts on that.
Yeah, I mean, dyscalculia is like another brain condition like dyslexia that makes certain areas of maths really hard for kids. And what we know about it is, first of all, kids' brains can change, grow, be rewired if they have dyscalculia, dyslexia, or other conditions. So we can do interventions with those kids that will change things. The other thing is, though, that for many kids with special needs, what's particularly difficult is something that isn't actually very necessary these days, which is the memorization of timed facts. And when we present kids with a much more visual and open math, and we have a video on our site that explains how to teach math facts visually, it is really powerful for those kids. So making math less procedural, it's what all kids need actually, and more visual will be really very helpful. Other?
Thank you.
Hi.
I had a question about your thoughts on the Kumaon Math Enrichment Program. How does that fit into all this?
Well, I can tell you that Kumaon say to parents that if children are found counting on their hands, counting on their fingers, they should report them to the instructor. So I don't think Kumaon's really based on what we know works for kids mathematically. I think it can be effective for some kids in improving test performance, but there are better ways to help kids understand and learn math. And what we want for all kids is for them to learn it conceptually with depth. We don't want them just doing more drill. You can improve some things with drill, but you're not going to make those kids into kids who really enjoy math and go on and do it for a long time.
What do you think about Khan Academy? I use it at actually in college level.
Khan Academy is an interesting one. I would say that I would not use it to teach kids math. It's an interesting resource for people who have learned math and need to go back and refresh up on things. But the trouble is, it's a very nice system, but ultimately is the most traditional math teaching. It is a man talking to you about math. And then you do short, close questions. I'm actually on Khan's advisory board, and he knows I think this about the... I think it's fine for some things, and for people who've learned maths and they need a review, or for people who are in a country where there are no maths teachers. But I would not use it to replace a teacher ever. I would not use it as kids' means of learning mathematics. There's no representations. It's not a deep, rich math experience.
Hi.
Hi.
Can you talk a little bit about testing? If you're teaching it in a bad way, do you test them in a better way with your method?
Yeah, I mean, testing has to change too. And if you go to our website, we have a whole section on assessment. One of the problems in math education in this country is we over-test kids. We test them over and over and over again. It's very hard to have a growth mindset when you're constantly tested and given negative messages through testing. So what we need to do is, we need to stop all of that testing. In math, there's more testing than any other subject. It's way too much. And what we want for kids is to think that they can grow and learn, and they don't actually need formal assessments until the end of a course, probably. And a better assessment to use during the course is more formative. Diagnostic feedback is many more times more powerful for kids than testing. So that's a big thing we have to change in the system as well. Well, one more question, I think. Sorry, I can answer others afterwards, but yeah.
Oh, so maybe I am class of '66, and
great.
because of some very nice, funny life things of mine, I have a 12-year-old daughter that I'm raising. Now, when I was a child, I didn't do very well in arithmetic. I couldn't remember. Geometry was just like breathing, but more joyful breathing. Right? I mean, it's so clear, so obvious, and so wonderful. And then that was it. Back to the nubbins. And when I came to Stanford, I wanted to be a physicist. I was terrific in science. But then I took a course in statistics taught by a graduate student who had been wrongly taught himself, I think. And I got an F. So I just gave up my dream.
Yeah.
Now my daughter is very good. She's visual. She's very good with science. There's a bit of a visual barrier about with some of the materials and the handouts and stuff in every different field, not just math. But then she's given up right now in her dream because she can't do the math. And I have a campaign to simplify it, do it visually, have one problem at a time so it's so logical and all this kind of thing. To do that...
She's 12?
She's 12. So to do that, I had to get up in midnight, sit down with the silly little things that are just really brain teaser type of things. And I knew I could do it by this time. And it's very thrilling. There are two things I think that you kind of touch on, but I think are very important. Learn that the struggle is there. It's wonderful. It's like being a wonderful, sweaty little fighter out there. And you don't have anyone there that will make you feel embarrassed. Oh, I can be loud if I want.
Yeah.
And the next thing is the thrill of getting through the struggle. It's like the top of Mount. Oh, but that is a huge thrill.
Yeah,
and
so
I feel that it rewires my brain. Every time I do that, something,
it's
like surgery inside here somewhere.
It is rewiring your brain. And it's terrible to hear of 12-year-olds who've decided they can't do math. And, it happens to so many girls and so many women. I've just read my latest application of Stanford students coming into my class. And I can't tell you how many of the young women had the words, I was going to do math and science until... And often it's a teacher saying something to them, just a single teacher or a single test score. So kids develop this idea they can't do math because they believe in the math brain and they believe that you can do it or you can't. It's very important to shift those beliefs in kids. Then they can struggle and realize that struggle is a good thing. And in fact, many of my undergrads who take my class say it really, learning this helped them get through Stanford and keep staying in science and math because they had to learn that everybody can do it and struggles are really good things. So it's really about changing kids' beliefs. And obviously we have to change the teaching kids are getting that are helping them think they can't do math. But changing what kids think they can do is really a key. I think we should stop because I think we've reached the end of the time. But I'm here and we have handouts for everybody with more advice and links and places that you might go to if you'd like more. So thank you.